Let's take up halides of group 16 elements. Elements of group 16 form three types of halides: hexahalides, tetrahalides and dihalides, where E is the element of group 16 and X is halogen. The stability of halide follows the order. Fluorides are more stable than chlorides, which are more stable than bromides, which are more stable than iodides, because bond length in case of fluoride will be less and bond dissociation energy will be high. That is why fluorides are most stable. Iodide being larger in size, so bond length will be more, bond dissociation energy will be less, and stability will be minimum. Amongst hexahalide, hexafluorides are only stable halides because fluorine is the best oxidizing agent and can provide energy for excitation of electrons. All hexafluorides are gaseous and inert in nature. They have octahedral structure with sp3d2 hybridization. Sulfur hexachloride is exceptionally stable due to steric reasons, and that is why it is used as a gaseous insulator in high power generators. This is the structure of SF6, which has sp3d2 hybridization and octahedral shape. All bond lengths are equal, 156.4 picometer. All bond angles are equal to 90 degree because they are in same planes. Amongst tetrafluoride, SF4 is a gas, selenium tetrafluoride is a liquid, tellurium tetrafluoride is solid. Reason is that surface area of SF4 is minimum, so minimum van der Waals force of attraction. Selenium has metalloid character, so SiF4 has got more surface area, more molecular weight, higher van der Waals force of attraction, hence it is liquid. Tellurium has metallic properties, so its fluoride is solid due to strong forces of attraction. These fluorides have sp3d hybridization and therefore should have trigonal bipyramidal structure, but one of the equatorial position is occupied by lone pair of electrons, and that's why they have seesaw shape. All elements except selenium form dichlorides and dibromides. These dihalides have sp3 hybridization and have tetrahedral structure. The well-known monohalides are dimeric in nature, for example S2F2, S2Cl2, S2Br2 and Se2Cl2 and Se2Br2. These dimeric halides undergo disproportionation reaction, that is, they get oxidized as well as reduced. Diselenium dichloride undergoes disproportionation to selenium tetrachloride plus selenium is formed. Here selenium is +1 oxidation state. It is getting oxidized to +4 and getting reduced to 0 oxidation state. Sulfur, selenium and tellurium form hexafluorides showing the maximum valency of 6. They all have sp3d2 hybridization, and hexafluorides possess octahedral structure, but these are colorless gases, and SF4 is extremely inert due to steric reasons. SeF6 is slightly reactive, whereas tellurium hexafluoride is hydrolyzed by water. It means it is comparatively more reactive. TeF6 reacts with 6 water to form 6 HF and H6TeO6. Sulfur, selenium, tellurium and polonium form tetrachlorides and bromides, while tellurium and polonium also form tetraiodides. All tetrahalides possess trigonal bipyramidal structure with sp3d hybridization, and due to presence of lone pair they have seesaw shape. 4 unpaired electrons form the bond with 4 halogen atoms, and one position is occupied by lone pair. This is the structure of SX4 or SF4, which has got seesaw geometry. This position is occupied by lone pair, and this is equatorial position. Repulsion at equatorial position will be less. That's why lone pair will preferably occupy equatorial position and not axial position. We call it seesaw shape. All elements except selenium form stable dichlorides and dibromides. Diiodides are not formed. Dihalides form tetrahedral molecules due to sp3 hybridization with 2 lone pair of electrons. That will result in bent molecule. The bond angle is less than 109 degree 28 minutes due to presence of lone pairs. Each have two lone pairs. The bond angle is 103 in HCl2, 101.5 in OF2, and 98 in tellurium bromide, TeBr2. Dimeric monohalide as S2F2, S2Cl2, S2Br2 are known. Their structure is similar to hydrogen peroxide. This is the structure of S2Cl2. Their bond angle is 104. Next we are taking dioxygen. Preparation: dioxygen can be obtained in the laboratory by the following ways: by heating oxygen containing salts as chlorates, nitrates and permanganates. First we are taking 2 KClO3 on heating in presence of MnO2 gives you 2 KCl plus 3O2. Here MnO2 is acting as catalyst. If we don't use MnO2, then the reaction will take place at high temperature. But if we use MnO2, the decomposition can take place at lower temperature. In this reaction, we have to be careful. MnO2 is black in color. If it is mixed with charcoal as an impurity, it may cause explosion. So MnO2 use should be free from charcoal as an impurity, otherwise it may cause explosion. Instead of this, if we heat KMnO4 to prepare oxygen, that is the safest method which we will take up. From oxides, by thermal decomposition of oxides of metal which are low in electrochemical series, and higher oxides of some metals also decompose to give oxygen. First example we are giving of lead dioxide. Lead dioxide decomposes to form lead monoxide plus oxygen. Now why this reaction takes place? Pb plus 4 is unstable, rather Pb plus 2 is more stable due to inert pair effect. That is why that Pb plus 4 has changed to Pb plus 2 very easily by gaining electron. So it gets reduced to Pb plus 2 plus oxygen gas is generated. HgO, red color HgO, mercuric oxide at 450 degrees centigrade decomposes to form mercury liquid plus oxygen gas is formed. Silver oxide is unstable. It decomposes at 350 degrees centigrade, liberates oxygen along with silver is formed. Manganese dioxide, if heated alone, it will change to Mn3O4 plus oxygen gas will be formed. Red lead, Pb3O4, on heating gives lead oxide plus oxygen. Reaction takes place around 600 degrees centigrade. Barium peroxide on heating gives barium monoxide plus oxygen gas. MnO2, if we treat it with sulfuric acid, it will give MnSO4, that is, it gets reduced to Mn plus 2, and plus it is formed 2 water plus O2 is formed. Na2O2, sodium peroxide, when reacts with 2 moles of water, it changes to sodium hydroxide plus oxygen gas is liberated. From salts, we can get oxygen gas. For example, sodium nitrate on heating gives sodium nitrite plus oxygen is formed. Exactly in the same manner, potassium nitrate on heating gives potassium nitrite plus oxygen. Potassium dichromate on heating gives potassium chromate plus chromium trioxide plus oxygen is liberated. Potassium dichromate is an orange color solid, whereas potassium chromate is yellow color solid. Chromium trioxide is a green color solid and oxygen gas is liberated. 2-KMnO4, KMnO4 is purple in color. On heating it gives K2MnO4 which is green color solid plus MnO2 which is black color oxide plus oxygen gas is formed. Potassium chlorate, if heated alone without MnO2, the temperature will be high, that is 400 degrees centigrade. It decomposes to form 2 KCl plus 3 moles of oxygen. KMnO4, when reacts with sulfuric acid, it forms K2SO4 plus MnSO4 plus 6 water plus 5 oxygen is liberated. Potassium dichromate also, when reacts with concentrated sulfuric acid, in both the cases we are using concentrated sulfuric acid, we get 2 K2SO4 plus 2 Cr2SO4 whole thrice plus 8 water plus 3 oxygen. 2 KMnO4 plus 3 H2SO4 plus 5 hydrogen peroxide. So we will give you K2SO4 plus 2 MnSO4 plus 8 water plus 5 oxygen will be formed. Laboratory preparation, we can also heat potassium chlorate and it can undergo disproportionation reaction to form potassium perchlorate plus potassium chloride is formed. This is on strongly heating. If we heat KClO4 further, we will get KCl plus oxygen. So ultimately we can get potassium chloride and oxygen gas at 650 degrees centigrade. So first potassium chlorate changes to potassium perchlorate and potassium chloride, and potassium chlorate on further heating gives potassium chloride and oxygen gas. So this reaction can be used in laboratory for preparation of oxygen. So earlier we had prepared it from potassium chlorate, which we had written in one step. Here we have written the same reaction in two steps. Hydrogen peroxide is readily decomposed into water and oxygen by catalysts such as finely divided metals or manganese dioxide. In this case, heating will not be required. Hydrogen peroxide decomposes to water and oxygen slowly. But if we add catalysts like manganese dioxide, it will decompose faster without heating. So if you want to prepare oxygen gas without heating, this reaction by using catalyst MnO2 can be used. On large scale, it can be prepared from water or air. Electrolysis of water leads to release of hydrogen at cathode and oxygen as at anode. Hydrogen is liberated at cathode because it is electropositive in nature. Oxygen is liberated at anode because it's electronegative in nature. And volume of hydrogen formed would be double than that of oxygen because water contains hydrogen and oxygen in the ratio of 2:1. Manufacture. From liquid air, oxygen is obtained by fractional distillation of liquid air. Liquid air is mixture of mainly liquid nitrogen and liquid oxygen, and there is a difference in their boiling point of 12.8 degrees centigrade. Therefore, they are easily separated by fractional evaporation when nitrogen, being more volatile, escapes first and oxygen gets separated, which we can get it collected. Nitrogen has got molecular weight 28, so it has less surface area, less van der Waals force of attraction, lower boiling point. Oxygen has higher molecular weight, more surface area, more van der Waals force of attraction and higher boiling point than nitrogen. By electrolysis of water, pure oxygen can be obtained by electrolysis of either acidified water using platinum electrodes, which are act as inert electrode, or alkaline water using nickel electrodes. In an electrolytic cell, we will get oxygen and hydrogen. This method is used in those countries where electrical energy is cheap and we need pure oxygen and pure hydrogen. Physical properties of oxygen. Dioxygen is colorless and odorless gas. Its solubility in water is 3.08 centimeter cube in 100 centimeters of water. That is around 3% at 293 Kelvin, which is just sufficient for vital support of marine and aquatic life which take dissolved oxygen from water. It liquefies at 90 Kelvin and freezes at 55 Kelvin. Oxygen has 3 allotropes, 16, 17 and 18 are their mass number. These isotopes differ in number of neutrons. Oxygen 16(8) has 8 neutrons, this has got 17 has got 9 neutrons and 18 isotope has got 10 neutrons. So they differ in neutrons but they have same number of electrons, protons. Therefore their chemical properties are same but physical properties will be different. Reaction with metals. Sodium reacts with oxygen to form sodium monoxide. Here if we take excess of sodium, we get sodium monoxide, but if we take 2 moles of sodium, we will get sodium peroxide. Calcium can form only monoxide, so calcium reacts with oxygen to form calcium oxide, which is monoxide. Sodium, potassium, rubidium can further combine with oxygen to form peroxide and superoxide. Lithium forms only monoxide, sodium forms peroxides, whereas potassium, rubidium and cesium form superoxide. Reason is that larger cation can stabilize larger anions. Magnesium reacts with oxygen to form magnesium oxide, which can form only monoxide. Aluminium reacts with oxygen on heating, forms aluminium oxide. Iron reacts with oxygen to form ferric oxide. Dioxygen directly reacts with nearly all metals and non-metals except some of the noble metals like gold and platinum and some noble gases. Calcium reacts with oxygen to form calcium oxide. Phosphorus reacts with oxygen to form P4O10, which is dimer of P2O5. Calcium oxide is a basic oxide. P4O10 is acidic oxide. Carbon plus oxygen gives you carbon dioxide, which is also acidic oxide. Oxygen is required for roasting of sulfide ores. 2ZnS plus 3O2 gives you 2 moles of zinc oxide plus 2 moles of sulfur dioxide. Oxygen is essential for combustion of hydrocarbons and carbohydrates as well as fats. Methane reacts with 2 moles of oxygen to form CO2 plus 2 water. Nitrogen monoxide readily gets oxidized to nitrogen dioxide in atmosphere. Nitrogen monoxide is a colorless gas, whereas nitrogen dioxide is brown colored gas. Nitrogen monoxide is neutral oxide, whereas nitrogen dioxide is acidic oxide. Some compounds are catalytically oxidized. For example, 2 moles of SO2 react with oxygen in the presence of vanadium pentoxide to form 2 moles of sulfur trioxide. This is the reaction taking place in contact process for manufacture of sulfuric acid. Second one is Dickens process. 4HCl plus oxygen in presence of catalyst like cupric chloride, we get 2 chlorine plus 2 water. So this reaction is called Dickens process, used for manufacture of chlorine. This is the first reaction of Ostwald process, which is used for manufacture of nitric acid. 4NH3 plus 5O2 gives you 1073 Kelvin. Using platinum as a catalyst gives 4 moles of NO plus 6 moles of water. This is the structure of oxygen. Oxygen forms double bond between another oxygen atom. 2 lone pair of electrons on each oxygen are left. Oxygen is paramagnetic in nature due to the presence of unpaired electron in anti-bonding orbitals. Reaction with non-metals. Most of the non-metals react with oxygen under high temperature to form respective oxides. Water reacts with oxygen at 1073 Kelvin or in the presence of electric discharge to form water. Nitrogen reacts with oxygen at 3273 Kelvin to form nitric oxide. Sulfur reacts with oxygen on heating or burning to give sulfur dioxide. Carbon reacts with insufficient amount of oxygen to form carbon monoxide. Carbon monoxide is neutral oxide, nitrogen monoxide is neutral oxide, sulfur dioxide is acidic oxide, and water is amphoteric oxide.